Hello, everyone. I'm Zohaib, as already introduced. I'm from DoorDash. I'm a technical lead at DoorDash. I know it's late. It's the last session, so I promise I'll keep it interesting. So, a little bit of introduction about myself. I've been invested in Redis itself for quite a long time now. Um, I still remember around 2010 when the NoSQL boom was all up in the air. That's where I discovered Redis, but I kind of initially rejected it, saying, "Oh, it's probably just a buzz thing." But then, while solving problems, I really felt like, oh, if I can have like nested dictionaries, sorted sets, and all these data structures, that would be really nice. And that's where I came across like, hey, Redis does that for you, and it gives you comparable speeds. With at that time, Memcached was the go-to place for everyone to do these kind of caching operations. So Redis did give a parity, feature parity, plus some speed advantages. I love open source. I spend most of my time exploring them, looking at the code, trying to understand and develop my taste around like what's good and what's bad. And just to show you the type of work that I've done in the past with Redis. So I did this blog post, a journey to center of Redis in 2011. I have a really specific use case where I wanted to get a notification, a PubSub notification from Redis as soon as the key expired from the Redis key, like Redis key space itself. Uh, that is a feature right now that you can turn on by flags, but that feature was not there at that point in time. So it was way back in September 2011, and same goes for like I wrote a Lucene storage engine on top of Redis, uh, quote unquote, what Redis search is giving you to build kind of a searching capability, a free form text searching capability in Lucene using Redis. Uh, and here's the issue that I opened up. I did a pull request for the same key expire eviction notification. That got merged as a different PR with more options, of course, which is good. But you can see the date. It's like it dates back to like September 22, 2011. So my investment in Redis goes way back. So at DoorDash, we're using Redis pretty extensively. We use it across the stack. Like we're three-sided consumer-facing market. Like we have dashers, we have consumers, and we have our merchants. So we're trying to create a best experience for our consumers so that we can create a rich market space for our merchants. And sometimes, in order to achieve the numbers that we want to achieve, because hunger and being late on delivering food doesn't go well together. So, in order to achieve good numbers, we have to go through a lot of hoops. It's pretty hard sometimes. So, in this talk, what you're going to be seeing is it's a story of how we discovered the problems in our tail latency and how we worked uh, around different limitations to get ourselves the latency numbers that we wanted. It's important to keep in mind that you would hit these numbers once you hit a certain scale, which I hope all of you do. Unless you don't go, Redis is actually so fast and commands are so nimble, you won't see the effect until you hit a certain number of requests getting into the network and hitting Redis. So while you're hearing all the tools, all the buzz, everything around, this is kind of an anti-hero talk that gives you ideas around the things that you might be missing. It's like polishing under your drawers to make sure you squeeze every bit out of the performance that you can get from Redis. So how many people here have heard about Cache Stampede or Cache Tailstorm or Cache Miststorm? Okay. How many have actually witnessed it and tried to fix it? Okay. So for those who don't understand, not to worry, it's a pretty simple concept. Here's what it is. So I'm going to boil it down to like really simple example with two servers. So imagine like you have two servers. They're serving requests. Usual setup is you first check up Redis for your value. you get a miss, you go to database, read the value, populate Redis, and do your regular business. So in this particular scenario, what you see is I've kind of depicted the lifeline or the lifetime of the whole key in the Redis space. And at the bottom, while the key lives in the Redis, it's fine because every time the servers go to Redis, they get back a reply. It's perfectly fine. But as soon as the key expires, you can see the second server hits Redis, gets a note back saying, "Oops, I don't have the key." So it went to it went ahead and just goes to database to say, "Hey, okay, let's fetch the data." While it's actually fetching the data, it's quite possible one more of your server would get a request requesting the exact same data that you would have got as a hit from your Redis cache. Pretty typical scenario. But in this case, since the key is not populated, the server goes to Redis, says, "Give me the key." The Redis server is like, "I don't have it." The response goes back, and that server also goes to the database now. So if you pay attention, in your regular code, one thing that you're doing here is you're doing a duplicate read now. And the other thing that you obviously miss is you're doing duplicate writes into the Redis as well. So you paid the network cost not only once, but twice. So, and you can imagine during peak hours, just maybe like 50 nodes, 100 nodes, you're hammering your database down. Who remembers those spikes on your database that happens during these kind of scenarios? This is how it exactly happens. You're going to have a bunch of misses, and then everyone piles up on database to do the read. Exact same read. Yeah, it would be cache hit, but yeah, you still paid the network cost twice. So the key to remember in this scenario is, in fact, in all the scenario, in your head is network is your enemy. And once you go on network, you're going to pay some cost. So we want to avoid network as much as possible. So there are a couple of fixes for that. People have already deployed that, tried that, and it works. One of the fixes, oh yeah, sure, you'll get duplicate reads everywhere. And one of the fixes is that you use a random, I call it random ahead of time eviction, but it's also known as predictive expiry. So what you do is, just like in regular scenarios, if you see spikes on networks, you tend to add jitter by saying, "Oh, I'll just do a random, and random plus minus before this point in time, I will request my data." So it's pretty simple. So consider a key that's going to expire in a fixed random gap. So if the key was going to expire actually on Redis on, say, 60 seconds after this, on time t, we would say, okay, t minus 5, I would invoke myself in a jitter position. What you do is you take your timestamp. So if you want to use this technique, one of the things that you have to do is, as part of the storage of the value, you want to store the timestamp when it was stored. So now when you go and read from Redis, you actually say, okay, let's take the timestamp that I got from Redis, and I know the TTL on this key, and let's multiply a random with a gap and add it to this whole equation. So what it would do is, at random, it would trip over the expiry from now so that the machine is forced to go read from database, even though the key was not expired yet. So the trick here is, if one of the readers can actually go ahead and go read in from the database and then reload that value into Redis back with the updated timestamp, then rest of the people won't rush into Stampede situation. And that's exactly what we're trying to do here. So this is one of really typical schemes. You would just find it out there, a lot of articles, everything. Of course, we implemented this whole thing. And then we asked the question, can we do better? So it turns out, yes, we can. There is this paper. I would highly suggest everyone to go read this paper. I won't go into the details because it goes pretty deep into the whole proof of lemma and probabilistic stuff. I don't want to even open up that topic here. So the technique is pretty simple. This is what a log graph looks like. So the closer the value on x-axis is to 0, the lower the value on y-axis is. And the higher the value is closer to 1 on x-axis, the higher value of the log on y-axis is. So if I can combine these two, that's exactly what this paper suggests, you can do a pretty smart thing. So here's a simple implementation. I took the Python, this is like literally the Python code in our code base. I literally just took it out, pasted it here. So all we do is, in this function you can see, I have an entry coming in and the expiry time window. That's the window by which I want to do ahead of time eviction. So I can set it to like start this process 5 seconds ahead of time, 10 seconds ahead of time, 15 seconds ahead of time. It's up to you. And if I take the entry, you can see I take the entry, I split it up into expiry timestamp and value. Then I take the current timestamp, and then I do the log random and multiply it with the expiry time window. And then I literally take that predictive expiry gap and add it to my current timestamp. And if that timestamp is great, so you would see minus because log of something between 0 to 1 is negative. So it would go positive. It would automatically expire that value and evict it out of time. How is this efficient? Paper has, go read the paper. It has a complete lemma, like it has the complete mathematical proof of this thing that shows you how it's efficient. So that caters for the situation where multiple nodes are going across and trying to read from cache and then fall over back to database and prevent Stampede. But there was more to it. So turns out in a typical database application, in a typical web application even, this is a typical setup. In each application node, you have an L1 cache that's like an in-process cache that you keep with yourself. And then there is an L2 cache, and then you go to the database. So there's like 3 levels of cache. So if this Stampede can occur between L2 cache and database, it can occur between L1 and L2 cache as well, because we want to avoid network. Every time I switch out of application, I'm going on network. We want to avoid that. So we observed the same effect. We were implementing identity service, and there were these instances where a stream of bulk messages are being sent out, and it would just slam the server with requests, like 7,000, 8,000. And we were like, okay, how do we fix that? So in these kind of scenarios, you usually keep the L1 cache with you so that you don't pay the network cost every time for going to network, and have a really small window, like probably 5 seconds, 3 seconds, so that you don't do repeated reads on the same key. It's really, the probability of key changing in 5 or 10 seconds depends upon scenario, but in our scenario, it was really low. So we can keep that thing with us. So under high traffic, similar cache stampede or misstorm can be observed between L1 and L2 cache and so on. So it can trickle down as well. So I can reuse probably the same technique here, right? Why won't I employ the same technique here? I can do the same predictive expiry here. Turns out, this is something that we encountered before we encountered the scenario that I described you before. So we tried to solve this problem without reading research papers, looking at internet, and doing it like a typical developer fashion. You just try to solve it in your own way. And since we were running Kotlin coroutines, we had the luxury of saying, oh, I have a dictionary that I can access in parallel. I can do lock-in and everything. So we kind of tried to solve the problem at the application scope first. That's why you see the difference. But in this whole process, we discovered something interesting. Basically, we took inspiration from front-end world. So I've been full stack for a long time. I know a lot of techniques that I've used there in the past. So what I figured out here was, oh, you know what? I can use debouncing here. And some of you might be like, what's debouncing? OK. So it's pretty simple. Let's directly just show you how it's done. So every reader that's coming in would provide you a miss function saying, hey, in case I'm going to go read this key from L1 cache. If there is a miss, call this function, right? So that's a typical behavior. You try to read from L1, it misses, you go do read L2 or database or so on, right? That function that's invoked in case of L1 miss is, let's call it L1 miss function. So when invoked by a debouncer, you're going to say, oh, here's my key, read this key from L1, and if it misses, invoke this function. Who here has been working with promises, deferred, futures? Okay, lots of hands. That's good. So it would be really simple. So promises and futures, they're the abstractions that give you guarantees over like, hey, here's an object that you can share between these different threads or coroutines or go routines, or there are 5 different names, but in these different workers. And once it's resolved, all of them would get back a value. So what we did was the first reader that gets in quickly checks the L1 key in a small lock. If it gets the key, fine. If it doesn't, the L1 miss function is invoked. And that would immediately return back a promise and unlock the dictionary and unlock everything that it had lock on. Now the rest of the readers, when they come in, before actually going to network and invoking L1 function, they can actually await on this promise that was returned back to them. So 10 readers came in at the same time. One of them won and said, I'm going to go read from the whole database or L1 and populate this L1 cache. You guys wait on this promise, and the rest of them wait on this promise. So you effectively prevented the stampede that would have occurred on repeatedly reading from Redis on network, the same key again and again. So first, I just want to show you the interface, how simple it looks. It's much simpler when you put it in the code. So for example, in our case, we were catering for the menu. So I have a debouncer object. Then I have a function, menu item loader, that gets the key that it has to load. And then I say debouncer.debounce, here's the key, and I pass in my loader. So the async function would, if it's guaranteed by debouncer that the async function would be invoked only once. And once it's invoked, until the promise returned from that function is not fulfilled, everyone would be waiting on the same promise. So the implementation is literally a few lines of code. So I did a JS version of this. Literally like a pending board, we're keeping a state in there, we wait for that promise, and as soon as the promise is fulfilled, we delete that promise so that the next requests can keep going in. So after the cache miss, you actually do this whole thing. So combining this and the technique that I discussed before, we're avoiding Stampede. Oh, actually, so we actually wrote a simulator for this whole thing. So it's a JS simulator. The slides would be available, so you would be able to access it. You can actually tune different parameters in it and actually run the simulation. It does the whole simulation and shows you how much traffic or how much cache hits or misses you would be saving for yourself. One of the questions that I always ask is, like, if you discover this kind of thing, we should not be the only one who is doing it. Because if we're doing it, then we're doing something else that's wrong. And after Googling around a little bit, I did found Java has this thing called Caffeine Cache. I don't know how many people use it here, but it has this concept of loaders. That's the exact same thing over threads. We were not able to use it because I didn't want to use the thread locks on coroutines because it would lock down the thread. But other than that, the base concept, the base crux of the whole system remains the same. So, of course, we stress tested after we did the whole thing. So we had a gRPC endpoints. We were doing full, so the numbers that you're about to see, they're full read through. We go L1, L2 database, and this was for token verification. And L1 had a TTL of 5 seconds, L2 had a TTL of 10 seconds, and finally falling back to database. And we ran this test for around 1 minute. So the intention is to explicitly invoke all of these cases. So the test runs long enough for us to witness these things happening. We did use this tool called ghertz. Um, 2 pods, 60 seconds, 2,000 concurrent connections, go, without debouncing, and the cache Stampede optimization. We had around like average time of. Important part is look at the slowest time. It's like almost 8 seconds. Fastest time is good enough. Average is requests per seconds were like around 17,000. With these techniques in there, look at the slowest time, 578 milliseconds. So even we rammed the whole the 2 pods with like we just rained it with the requests. We were able to get pretty good results out of it, because most of them would be L1. Then as soon as the L1 is about to go out, there would be a predictive expiry on L2. So we reduced the traffic at every level, and we were able to squeeze some good numbers, 25,000, 21,000, almost 22,000 per second. The other problem that we saw is with the large values. So I've been listening to sessions. People cache fragments of HTML, machine learning models, all these different kind of things, and they're usually large values. So it could be pre-compiled payloads. It could be your JSON payload with message queues coming in. Now, when they're going to have the whole Redis streams and message queues relying on this, message queues are going to go in there. And we know very well how heavy usually these messages are. They do contain some payload in there. So we took a page from HTTP. We didn't want to reinvent anything at all. We literally took a page from HTTP. It's because the technique that we're about to exercise is, I wanted it to be like really well tested. Nobody should have objections on it. No questions asked, and we can roll it out in prod and test it. And we decided to use compression. We said, okay, for every large payload, we want to compress it. It doesn't look. It looks like it's an obvious choice. It was not that obvious, because when we were looking at these trace logs, and we were like, why is this taking so much time? And after inspecting some payloads, there were some suspicions around, oh, maybe it's a payload size. So we were also kind of experimenting initially with this whole idea. But the more we went into it, the more we were sure that it is the same problem. So considerations that we had to keep in mind was, like, we wanted to have a decent or a good compression ratio. I don't want to go extreme and have some compression that just minimizes the whole payload into a few bytes. I don't want that. The reason being, it won't be lightweight on the CPU. Like, I want to minimize CPU. We want to make sure we're not impacting the other threads, other CPU cores being affected by this. And we wanted it to be like really stable, because this whole thing is going to be like part of production pipeline. So if anything blows up, you're losing deliveries left and right. So one of the exercises that we decided to do was, we said, okay, let's benchmark different compression techniques. There are a couple of them in market. Fortunately, we have a tool for that as well. It's called LZ Bench. GitHub URL is there. There's a nice web UI as well. The thing with compression is it varies from case to case. It might not work. The same compression technique that I'm about to describe might not work really well with the binary blobs that you're serializing for your PyTorch models or something else. But it might work really well for JSON. And same holds true the other way around. So you have to pick and choose. And I would highly suggest, if you ever do this, do these benchmarks. Make sure you understand the impact of CPU usage and you understand the size of your payloads. So in our scenario, like, here's an example. Chick-fil-A, the menu that we're serving off the wire was like 64 KB. So imagine every time somebody loads Chick-fil-A menu, you're pulling down 64 KB from Redis. It's going to kill it. Same holds true for Cheesecake Factory. It's like 350. We've seen payloads up to 700 some KB, close to a megabyte. So it's pretty obvious. As soon as you start using cache intensively, again, you forget about cache is like a physical component in the middle, living on network. The rules of physics still hold true to that thing. The number of bytes that you're going to transfer is going to affect your performance. You can make network like 10 gigabytes still, sure, but you can do better. And this is exactly what we did. In our scenario, what we observed after running benchmarks were like the two compression algorithms that worked really well for us on minimal CPU usage is LZ4 and Snappy. They're both open source. Snappy is from Google. LZ4 is an independent open source project, been used pretty extensively in various other open source projects as well. Our observations was Snappy, like LZ4 was giving slightly higher, like really slightly higher, not much, compression ratio, but it was a decompression where it smoked it off. So decompression, it's really fast. And in our scenario, it's totally multiple readers, more reads than writes. So we opted for saying, oh, let's try them out. So we went with the LZ4. So as a proof of concept, what we did was, okay, I loaded some sample menus on my local host. So these numbers that you're about to see, they're running on my local host, no network involved. There's like literally nothing in the middle. This is the cheapest network call that you can make. So we did like 10,000 unique set operations and 10,000 unique get operations and repeated them over and over to get an average numbers. So look at the difference. Set without compression takes almost 16.5 seconds. With snappy compression, 12.6. With LZ4, 12.8. Get without compression, 12 seconds. With snappy, 7.5. With LZ4, 6.4. And these are averages. Like we ran it over like 10 or 20 times to average them up to make sure there's no noise in the middle. So you can already see the difference. Like if you look at just the get difference, it's like half, almost half. Like and we made sure that the menu payloads were distributed uniform as well, so that the payloads are even. Like I'm not doing heavy payloads only, I'm doing light payloads and heavy payloads. So a sample of 10,000 uniform random samples from menus. That's how we did that. So the results were pretty obvious. We wanted to just try it out and get it out. So results, as suspected, the diagram is kind of cheating, but it suddenly dropped from almost P99 of around 900, 800, all the way down to 750. And the spike that you see in the middle, that's the important part. In peak times, if there's a promotion going on or if there's some kind of heavy load coming in, you would see these spikes. With this technique and combining it with the ahead of time eviction, we were able to smooth out our P99 tail latencies around 750 milliseconds, worst case. The important thing is the storage, the memory used. So, of course, since we were storing compressed payloads, look at that drop. We went all the way from almost to 2 gigabytes to 1.7 gigabytes. You suddenly bought yourself 300 megabytes worth of space in your Redis key value store. So in conclusion, the important thing is that I think everyone should remember is Redis is really fast. The problem occurs when people use it, like Redis being ubiquitous has its superpower and its curse. The superpower is, yeah, I can use it on almost any scenario and start moving a lot of my data into Redis. But the curse is, if you don't pay attention to the details, you would get slammed and you would still scratch your head over, oh, what did I do wrong this time? Turns out it's not Redis' fault. It's not fault from Redis or the software itself. It's you who's not paying attention to what's going on under the hood. So instrumentation, measurement, and making sure you experiment and deploy the right thing is the way to do it. Thank you. For any questions?
You just mentioned compilation. So how Redis work with compilation?
Oh,
Compilation, yeah.
yeah.
How
So
it work?
before doing the set command, the idea is before doing the set command, you actually compress your payload. So if you were about to serialize, say, a JSON payload, you compress it down, and then you send it over to Redis. So you store compressed payload in your Redis store. The only caveat is then if your services are like polyglot or like you're in different technologies and multiple consumers are consuming it from cache, they have to understand the same compression. People use different techniques. Like some people even use zlib out of the box. That works, but yeah, I can see a hand there. But in my case, I just wanted to be like really sure about that it's not going to impact CPU. There are like even Cloudflare for their message queue started compressing their payloads with Facebook's ZSTD compression algorithm, and that worked really well. So like just take a page off from like what HTTP does. When it's shipping over the wire, make sure it's compressed. I hope it becomes a feature sometimes in Redis where you can specify every transaction going along is compressed.
Okay, any other question? No? Thank you.
Yeah.